Spherical, a particle in spherical shell. Here we are dealing with a particle of mass m can move freely inside a shell, a volume delimited by two infinite spherical well of radius r1 and r2, where r2 is equal r1 plus c, which is bigger than r1. Here we have a particle that is confined in this shell. So the confinement fact, that means there is kind of discrete energy allowed for this particle to have. The first question we will deal with this. We need to calculate this energy level, and then we need to find the normalized wave function with zero angular momentum. One very important remark here, that we are also dealing with symmetry, spherical symmetry. That means there is no dependence on theta and phi, and there is only dependence on r. That's give us a hint to start from the radial Schrödinger equation, which is minus h bar over 2m d square over d r square ur plus v effective, which is collection of two terms, vr plus something, a function of L, ur equal e ur. So since we have spherical symmetry, then we take it's enough to consider L equals 0, and then we have this equation. We have this equation where is L equals 0. I have just vr ur equal. Then also we need to consider something else if we need to solve this problem. If we need to solve this equation in the shell where is no potential, then also vr equal 0, and then we have just this a simple differential equation where is the constant 2m over h bar square multiplied by e equal, I call it k square. And as usual, the solution of this problem, this equation is ur equal a e ikr plus p e minus ikr. That means there is combination of two propagating wave in opposite direction. To determine the constant a and b, as usual, we need to use the boundary condition. The boundary condition, we have two boundary conditions. ur should be equal 0 when r equal r1 and r equal r2. So I have two boundary conditions and I have two constants. By using these two constant boundary condition, we can find two relationship between a and b. A over b equal minus e minus e to the power minus 2i kr1, and also a over b equal minus e to the power minus 2i kr2. So there is equality. So I have new equation, but here we need to show that this equation actually is complex equation. It's clear that I have just Euler form of complex number, which is the exponential to something imaginary. So I have to solve it in complex analysis, not in real analysis. That means I don't have one solution. I have infinite solution, and the only difference between any two solution is integer of 2 pi. As a result, as 2kr1 equal to 2kr2 plus integer of 2 pi. So in this, we can, using this solution, I can get a relationship of k as a function of n, and also the difference between r1 and r2, which is called as psi. So k equal to pi n over psi. But as previously, I know that k, there is a relationship of k as a function of E, the discrete energy, which is k square equal to me over h bar square pi equality. This is also equal to p square n square over c square. So I have now I can find en as a function of n, which is h bar square p square over 2m fc square multiplied by n square. So now this is the discrete energy formula. Now we need to find the normalized wave function. Normalized wave function, that means I need to find psi as a function of theta and r and phi. I have that just ur, and this ur could be rewritten somehow because I know already a and b. I just inject a as a function of b, the other constant, and I can get ur equals c, which is constant, multiplied by sinus p over c n r minus r1. From ur I can just jump to r by dividing over r. Now I need to take into consideration that L equals 0 and M equals 0 because I have this symmetry, spherical symmetry. Then psi theta, psi r theta phi equal to u when L equals 0, which is 1 over square root of 4 pi, multiply by r, which is I already found, say c over r sine something. The new constant I can call it c prime if, to simplify the life. So now to find this c prime, this constant, this I need to use the normalization. That means the particle is somewhere at any moment. It should be somewhere in the shell. So the integration over this volume of the amplitude, the square of the wave function, should be equal to 1, which is represent probability. And now I take that spherical symmetry. That means the integration over theta and phi is just 4 pi, and I can then there's just one integration to be calculated, which is the integration between r1 and r2 of sinus square, which is very easy to solve. And then finally I have the value, the numerical value of the constant. In the second part of the problem, I need to use approximation. This approximation says that psi is very smaller comparing to r1, very smaller than r1. So in these cases, I can approximate the centrifugal potential as a constant, and this constant could be considered as 0, shifted to be 0, without changing anything about the physics of the problem. This constant is corresponding to this value at r1 plus psi over 2, and then I need to compute the energy with generic angular momentum under this approximation. To solve this, I need to start from general radial Schrödinger equation, where there is L, and then I can inject that VR equals 0, because VR is equal to constant, but could be shifted to be equal 0 without changing anything about the physics of the problem. Finally, I can get this equation in the black squared bracket, and where is r, there is minus h bar square over 2m d square over dr square ur plus h bar over 2m l plus 1 over r square ur equal e ur. So I have r 1 over r square. But how can I use this inequality, this approximation, in order to inject it? In order to do that, I need to find a corresponding inequality from this, where I can introduce r instead of r1 or r2 or psi. I know that psi is equal to r2 minus r1, but r2 minus r1 is the limit value of r minus r1. So r minus r1 is always smaller than r2 minus r1, or equal. But r2 minus r1 is equal to psi, and psi is very small comparing to r1. So I can find finally this inequality in the black books. R minus r1 is far smaller than r1. Now I can use something 1 over r square is equal to 1 over r minus r1 plus r1 square. I can get r1 outside of the bracket. So 1 over r1 square multiplied by 1 over 1 plus r minus r1 over r1 square. So 1 over r square is 1 over r1 square multiplied by Taylor expansion. By taking just zero order, I can consider 1 over r square is approximately equal to 1 over r1 square. So I can get this equation, where is r1, which is constant, minus el, that is constant. I mean, here we have constant minus h power over 2m, the second derivative with respect to r, ur of ur, plus some new constant multiplied by ur. This constant, I can call it minus e, or just put it in the second part of the equation and it will be e. So, and this very similar to the previous equation in the first question of the problem, the first part of the problem. So I found it that it is h bar by similar procedure. I can find the value of e now as also equal to h bar p square n square over 2m c square. By playing, I can get el is equal to the sum of two parts. The first is the previous one, the new one plus the new one with depends on l multiplied by l plus 1. Finally, I get this star relationship of e of generic with generic angular momentum. Let's now check the validity of this approximation. To check the validity of the approximation, I need to find the error. The error resulted from Taylor expansion. That means, let's take the first order, the zero order, and first order. What is the difference between the zero order and first order in Taylor expansion? Delta E, by just calculation, it could be found as something multiplied by 2r minus r1 over r1, which is approximately equal to h bar square over 2m r1 square multiplied by 2c over r1. So I have this, but using star also I can find what is the difference between two generic value of E. I change now N, not L, because the energy difference in L is bigger than. So En plus 1 minus En is equal to h bar square p square over 2m c square multiplied by 2n plus 1. And to this approximation to be valid, this value or this difference should be far bigger than the error resulted from Taylor expansion, which is h bar 2c over 2mr1. So using this inequality, I can find the condition where is the validity of this approximation is always true, which and this condition is 2n plus 1 should be far bigger than c to the power 3 over r1 to the power 3.